La seconda parte della lezione di 10 novembre, in cui continuiamo con lo studio, analisi di dati statistici, e dopo aver introdotto varie medie, I am switching to English, after introducing different mean values. By the way, I forgot to say that this mean value, M1, is called arithmetic mean value, while this mean value is known as metric mean value. But it is not so important, the names. Let us go further with the next quantity that we shall introduce. That is Mediana. You know what is a classical notion in geometry as mediana. This is different from the notion of mediana that we shall use now. By the way, I forgot to ask you if you had a question from the first part. Start to go further, but if you have some questions or via chat or immediately ask me. The next quantity is not mediana. In English, median. This quantity is slightly different from the quantity that we already introduced. So, what we have? We have kind of data. 1, 2, n. Here we have F1, F2, and so on, some table F. What we have to do? Usually these data are not ordered as increasing or decreasing. So as we made our frequency graphic before, we had kind of oscillating graphics. And our first step from here is to order this data in such a way that we have G1 smaller than G2, smaller than, and so on, smaller than Gn. So first, we reorder, have to reorder our data in such a way that they will be increasing. For example, we have, for example, this data. 5 times we have the number 3. Then we can interpret what is this 3. 6 times we have the number 4, and 7 times we have the number 6. For example, we can interpret in such a way. This is our frequency, the note. One of the notes, this do, si, la. La appears 3 times. This appears 4 times. 7 appears 6 times. So our first, this is the times that this number appears. So practically our F1, F2, we have to represent in the following way. We have 5, 5, 5. 3 times. We have 6, 6, 6, 6. And then we have 7, 7, 7, 7, 7. How many times? 6 times. This is our F1, F2, F1. As you can see, they are represented in such increasing number. We do not need to our quantity. We simply say this is F1, F1, this is F2, F3, F4, last is 7, F7, no, F3, no, 7, here is 7, here 8, and the last is F. How many we have in total? 3 plus 4 is 7 plus 6, 30, F30. So our F1, F2, F3 are represented in such a way, and we do not need to reorder. This is our sequence. How we build now the median? Here is the rule. Once they are ordered, the mediana is computed in the following way. Cases. First case, when this n is odd number, n is 2 kappa plus 1. What it means? This means that we have to put G1, G kappa plus 1, and then in the middle, we have G kappa plus 1. And then we have G kappa plus 2 up to G 2 kappa plus 1. So we take simply this number, G kappa plus 1. This is our median, the number that stays in the middle of our sequence. Why is when n is 2 kappa, of course, we cannot say that we have in the middle a number. We have two numbers. For example, if if we have F1, F10, what we have in the middle? If we have F5, F6, what is F5? If this is 2K, this shall be F. So we have G kappa, GK. What is the next one? G kappa plus 1. Both guys are in the mid interval. And we take these two guys and take their mid. So this is the definition of our median. We have to distinguish two cases. When we have, for example, start from F1 up to F11. This is the case of odd n. Then we have immediately, we can say F5. Sorry. Yes, we take kappa, F5 plus 1 is F6. So we take F6 is in the middle. So here you have 5 numbers. Here you have other 5 numbers. And in the middle is F6, this G kappa plus 1. If instead we have even number of data, we take this in the middle, in the mid two numbers, these two numbers, which are G kappa plus 1, and take the arithmetic mean. And this is the definition of the median. So in our example, this is our example, let us compute the median. In our case, we have F13. So n is 13, odd number. Our kappa shall be 6. So we have to take F7. What is F7? Already clear. It is 6. So if you have ordered well the data, remember, if they are not ordered, first order them, and then you take, for case of odd number, the mid number, and otherwise you take when is even, you take the arithmetic mean of two mid numbers. Okay, so this is the example, this is the definition. Let me ask you if you understand well this part, or if you need some other question to be answered. If you have some question, please to pose your question. Okay, so we have media e mediana in italiano, mean value, means, and median in English, for different cases of data. Our next step is to take something that is very important, for example, we studied Kuramoto model with many oscillators. What is important for these oscillators to work in synchronization, this magic word, synchronization, how can be measured? Practically, the synchronization shall be measured, but one important quantity that also is important for statistical analysis, that is the deviation. So we have to take the next point in our statistical analysis. Data analysis, probably statistical still not. Okay. The next quantity, variance and deviation. So variance is defined in a very simple way. Typically, if you have your 1, 2, and so on data ordered in this form, Fn, how you compute the variance of your data, F. For simplicity, we have all these data with one letter F, and we want to see what is the variance. The variance is defined in very simple way that is very similar to our second mean that we introduced. So what we have to take is Fj minus F bar. F bar, let us call, is M1 of F that we defined as arithmetic mean. So if we take this F bar mean, so we have to take now squares in which from 1 to n. Then in our M2 mean, when we take M2 of F, we take sum of Fj square divided sum over j and divided by n. Here j varies from 1 to n, and then we took square root of 2. Now in the class we do not take square root of 2, and for specific technical reasons we do not divide by n, but minus 1. This is kind of technical. Think that for when you work with large data, and if you divide by n or n minus 1, what is the difference? The difference is n minus 1 divided by n, always for big N is approximately 1. So we cannot make between n minus 1, but this is the tradition. So I follow the book that I propose you and put in the variance this n minus 1. And another important thing, no square root. Why? because when you take the square root of the variance, you shall get the deviation. Therefore, this is the variance. And the deviation of f is simply root of variation of f, which is almost similar to our second mean value. That is sum of fj minus f bar divided by n minus 1, and then you take the square root. Of course, I make a comparison with this mean value, but take into account the fact that here we have not fj, we have j minus f. This means if our fj are different from f bar, so when we have some oscillations, especially in Kuramoto model, when we have oscillator, this is the quantity that is important for the synchronization. If this quantity with the data is smaller and smaller, then we can say, okay, we have very nice synchronization. Fj not constants, but they oscillate in such a way that deviation is very small. Therefore, this quantity is very important also for our statistical analysis, and also for the probabilistic approach that we shall follow after a while. So we shall have variance and deviation in our next lecture. This is one of the main tools we shall use. So probably we shall take some example, and let me say you that for practical applications, actually in the book, this quantity I don't know is by S. For me, deviation, natural letter to use is D. For variation, natural letter to use is V. But in the book, you have this notion, so different letters, but notion is very clear. Let us take one example that can be taken immediately. Here you do not need to order your fj. For example, if you have 1, 2, 3, and 4, and you take specific data, for example, 3, 2, 4, 5. Let us see the of our work for this example. This is F1, this is F2, F3, F4. So to find M1 of F, that is F bar. Can you see what is F bar? Yes? What is the mean value? We have 4 data.
Yes. It's 3.5.
Yes, half of the 7. So 3.5, this is 7 over 2, 3.5. Thank you. In order to find the deviation, we can say, let us find the deviation. We have to you have to compute from 1 to n. And do not forget to divide by n minus 1. So the first term is 1/2 square, 3 over 5. 2, this is plus 3 over 2 square. Then we have 4 minus 3, this is plus 1/2 square. And finally, we have 5 minus, this is plus 3 over 2 square. We have to divide by 3, and we have to take square root of 2. So here we have 1/4. 1/4 is 1/2. 9/4, 9/4, 9/2. So we have 1/2 plus 9/2. That is 10/2. It is square of 5/3. So if you help me with square root of 5/3 to have this precise, I shall be satisfied. Always for your written exam, you can use calculators, but don't trust too much calculator, because from time to time it is important to use the brain, and some of the problems, they do not need calculator. In this case, I agree. Yes?
It's 1.29.
Okay.
Nation.
1.29. Other students agree with this? If there's
Yes.
contradiction, okay, very good. So approximately you have a very small deviation, and as I told you, this means oscillations are around 0.5. This is 1.29, is relatively good oscillation. Of course, if you have more data, then you can use appropriate software to make this calculation. Now we need to go to the next important inequality. As for the mean values, also for relation, we have appropriate inequalities. This is inequality with the name of a Russian mathematician. I know especially for Italians, it is difficult to pronounce some of the Russian names as they are. For example, Chebishev is something that cannot be pronounced very, but with small modification, probably you can use it and know that this is important inequality in probability, in analysis in general, and it is connected with the name of this Russian mathematician, Chebishev. And we shall call this Chebishev inequality. Actually, Chebyshev inequality is connected with something connected with our deviation. Let's explain what is the problem treated by inequality. So you have your data that we called F1 up to Fn. We have this data. Sorry. Let's change F1 to Fn. So you compute, as we already did, the quantities F bar and deviation of F. That is called, in other words, SF. And then we want to see the following. You have our difference, Fi minus F bar. We compare, because absolute value of Fe minus F bar, this is the distance between our data, our measurement Fi, and the average F. So we want this to be sufficiently relatively small. For example, smaller or equal than this quantity S multiplied by kappa. And we want to see kappa 1, 2, 3, and so on. We can count how many J's satisfy this inequality. This practically means the following. Take our data that we already put in kind of graphic representation. Then you compute your average F bar, and then you take your deviation, compute S, and you want to see, okay, in this interval, that is interval around F with length kappa times S, where S is the deviation. When you try to move kappa, how many points are in this slab? How many points shall be satisfying, how many points J satisfy this inequality? So usually number of elements in a set, number of elements, mathematical notation is the following: numbers of those J for which Fj bar is smaller than kappa S. Now we want to see what kind of inequality is satisfied by this quantity. So Chebyshev inequality measures this quantity, and for simplicity, all this J, we can denote this set as S capital depending on kappa. Because here J varies, and we have a set of those indices, J, for which our data are close to the mean value. And we want to estimate this, the number of S kappa, the number of elements of S kappa. So the inequality that we shall is the following: Chebyshev inequality lemma. If I divide by n, this is bigger or equal. Actually, in many cases, we shall have strict inequality. 1 minus 1 over kappa. And as you can see, this is kappa squared. Sorry. As you can see, the is quite useful because actually this number is independent of the deviation, this lower bound. This means if we measure these elements, in any case, this is not zero. This shall be according to this kappa. We shall have really, for example, when kappa is 10, then we shall have something that is very close to 1. This means almost all data shall be in this strip. Practically, we have horizontal strip. And this means this goes to 0, and this means all S kappa, because finally J when varies from 1 to n. The optimal case is number of this S kappa is n. But when n divided by n is given, then this shall be exactly 1. So this inequality shows that our S kappa has really some elements that can be measured and evaluated. And here is the role of this quantity of the deviation. So the proof of this inequality is quite simple. So we shall try to prove it. And with this, today we shall think this shall be, how to say, the end of our analysis of data. And we shall see that similar idea for this for probability treatment appeared again. So understanding this part, we have a good basis to understand the next part. So how we prove this? Of course, we use the deviation and take the square of S kappa, the of S. If I take S square, by definition, square, this is sum of Fj minus F bar squared. I shall put n minus 1 here, n minus 1. So, this is idea of the proof. And in this, can you see here, or I shall switch a little bit? Okay, probably you see better now. For the proof, we start with the definition of the deviation. I again use the notion from the book. In this way, you shall probably, if you use the book, you shall understand better. So, this is the sum over all where varies j from 1 to n. But now we have S kappa. S kappa is subset of this 1 to n. So first I shall take j in S kappa, and then I shall take the sum j outside S kappa, but j between 1 and n. I forgot to say that also here, j would be, of course, here, j is integer between 0 and 10, but this is, if I take fj, this means j is between 1 and 10. And then we have other squares, fj minus f bar. Of course, this shall be bigger or equal. Once I applied the definition of the deviation, I shall clean the definition. It's already applied in order to complete the proof of the lemma. So I said this is positive. I shall replace by 0. So we have sum j in S kappa, fj minus f bar squared. Actually, there is important thing that we didn't take into account. So, actually, the important thing here is not S kappa, but because in S kappa we have inequality from above. Actually, here we shall use the fact that outside S kappa gives opposite inequality. So we have fj minus f bar bigger or equal than kappa s. So in this case, we simply shall neglect S kappa, and we shall say that this is bigger than j is not in S kappa, but I can replace this by some j not in S kappa, and here we have kappa squared S squared. I think till this moment we have the correct inequality, and now we have to what is the relation. If I take j in S kappa, this set, and j outside S kappa, but between 1 and n, n. What we can say about these two sets? Of course, they are complementary sets, and if we take the union shall be n elements. Therefore, if I take number of these elements plus number of these elements, I shall get roughly n. This is important inequality and enables me to find the number of elements here. So the number is n minus the number that I want to estimate. So this is equal n minus number of elements in S kappa times kappa squared S squared. Let me ask you if this inequality is understood well. If you have here of j in some set, and in the sum you have the same element, you put this number outside, and the sum of 1 practically is the number of elements in this set. But the number of elements in complementary to S kappa set is n minus the number of elements in S kappa. So I use this relation, and I get this quantity, and as you see here I have S squared, here I have S squared. This is small s, the deviation, and I have not really can make a cancellation. So if you now divide by square f square, kappa square s square, what we shall have? N minus 1 divided by kappa square is bigger or equal than n minus the elements of S kappa. I can rewrite this inequality in the form that is required in Chebyshev inequality. So I put number of S kappa on the left and the other guys on the right. And from here I get the number of S kappa equal n minus 1 over kappa squared. Okay, and now we are ready because Chebyshev inequality requires number of kappa divided by n. So I have to divide by n. So this shall be divided by n. And you see, n divided by n gives you 1 minus n minus 1 over n kappa squared. This guy is smaller than 1. N minus 1 over n is smaller than 1. So we can put other inequality, strict inequality, replacing this guy by 1, and we minus 1 over kappa squared. So Chebyshev inequality, that was the purpose of our work on this whiteboard. So please to take for a while look at the proof and tell me if you understand the proof of Chebyshev inequality. If you have some doubts. And see again the registered lecture, and if you have some problems, observations, we can treat them in our next appointment. I think with this to stop our lecture today. This is 10:45-46, therefore as it is planned, we shall have tomorrow the next appointment. Let me stop the registration to register the lecture and then ask you what we shall do tomorrow. One moment. Let me stop.